Okay, so if I sound like I'm a little winded, I was just in a pretty big ping pong tournament, so not really. It was just between me and my husband, and I lost, so I was a little winded. All right, so this says that the displacement of the wave traveling in the positive x direction gives the displacement equation. It says what's the frequency, wavelength, and speed of this wave. So, um, this, of course, is the A. This is the K right here. This is the angular frequency. So the frequency is like this. So you've got 124 radians per second divided by 2 pi is equal to, 19.7 hertz. And then the wavelength is equal to 2 pi over k. So 2 pi over 2.7 is 2.33 meters. And then the wavelength is equal to velocity over frequency, which if you rearrange to solve for the velocity here, then you end up with the frequency was 19.7, wasn't it? So you end up with 46 meters per second. Okay. All right. Next one is the phase difference. So for this, remember we had this equation, and wavelength is equal to velocity over frequency. The velocity is 343 meters per second divided by 200 hertz equal to 1.715 meters is equal to 2 pi times the change of position is just that 0.8, meters divided by 1.715 meters, which ends up equaling 2.19, I believe, radians, not this 2.93. So I don't really know where I got that. Oh, no, it is. It is 2.93. What in the world am I saying? 2.93 radians. Alright. And then it says what's the amplitude, frequency, and wavelength of the wave for number 14. So, again, I don't have the book here, but it gives all of that information right here. If you have a question on that, I guess, let me know. And then here's another one of those weird ones where I've done something else, but I don't know the question to it. So I'm going to have to look for that one and the other one that I did, that I said was maybe another one. So skip this one for a minute. I might have to do another video for that. This one says that the sun emits electromagnetic waves with a power of 4 times 10 to the 26 watts. Determine the intensity of the electromagnetic waves from the sun just outside the atmosphere of Venus, the Earth, and Mars. Okay, so this is one of those that you have to do the intensity. And it's like the power of the source divided by the 4 pi r squared. So there was an equation that we had in our PowerPoint that had to do with like spherical intensity, and so this would be like that because of course planets are like spheres. So the radius of the Earth, you need that, is 1.496 times 10 to the 11th meters. The radius of Venus, 1.082 times 10 to the 11th meters, and then the radius of Mars is 2.279 times 10 to the 11th meters. And the power it gave was 4 times 10 to the 26th watts. So you just do that for all of them. So for Earth, it's 1400 watts per meter squared. For Venus, it's the 2700. And for Mars, it's the 610. And then last, we have it's saying that this friend of yours is loudly singing a single note of 400 hertz while racing towards you at 25 meters per second. On a day when the sound of speed is 340 meters per second, it says, what frequency do you hear and what frequency does your friend hear if you suddenly start singing? So for the frequency of what you hear, that's someone is approaching, you're stationary, you've got this 1 over the velocity of the source divided by the v, so you've got their 400 hertz divided by 1 minus their velocity as they're approaching you divided by the velocity of the temperature, the sound in the specific temperature. So it ends up being 432 hertz. And then if you start singing, whoops, I wrote that a little bit wrong. So you end up using this equation then whenever you start to sing. So you end up with 429 hertz for that one. Okay, like I said, I'm going to have to go back on a couple of those because the questions that I decided to do, I have to find. So go with this for now, and if you have